Do you know what's in meringue? Because I'm just egg white and sugar.
Yeah,
that's it. That's the entire thing.
Yeah, it's the
Temperature. It's a concept all too familiar to us. In everyday life, temperature is an omen of muggy afternoons, of frigid nights, or of criminally rainy days. In the scientific world, temperature controls chemical and physical processes and dips into physical extremes with the power to seemingly defy gravity in the fabric that holds matter together. But in simple terms, what is temperature? Let's first start with the definition of energy. Energy is the ability to do work. In other words, energy is the power for one piece of matter to affect another. Energy can come in the form of potential, kinetic, electrical, chemical, nuclear, or thermal energy. Thermal energy, or heat energy, describes a form of energy that is part kinetic and part radiative. Any particle that vibrates is a particle with heat energy, and it is this kinetic component that we'll be focusing on in this video. When a particle vibrates next to any neighboring particles, the particle will tend to transfer any energy between itself and the particle, until both particles of matter are vibrating or bouncing around with the same amount of energy. This exchange of thermal energy between particles encompasses the concept of temperature. Encyclopedia Britannica states, temperature indicates the direction in which heat energy will spontaneously flow, that is, from a hotter body to a colder one. And it has the following definition for heat as well: energy that is transferred from one body to another as a result of a difference in temperature. Particles and bodies of matter have thermal or heat energy as long as they vibrate or bounce around, and if they possess thermal energy, then we can measure it and assign it a value to indicate its temperature. I reckon we're pretty familiar with what these temperatures look like: 32 degrees Fahrenheit, 0 degrees Celsius, or 273.15 Kelvin. Each one of those temperatures contains information about how excited the particles of the system are, about how fast on average each particle is bouncing around into every other particle in the system or body. Yet there's a measurement at the heart of this video that defies the definitions of heat and temperature. It shows up every year, merely posing as a temperature when the leaves start yellowing and the temperature starts falling. I'm talking about
your wind chills.
Wind chills. Wind chill.
Bad wind chill. Wind chill.
Wind chill advisory goes into effect this evening for the entire area.
Whether you're outside or not while watching this video, chances are that your body is currently at a stable 98 degrees Fahrenheit. If you're outside and it's cold, the mitochondria in your cells are firing up and burning fuel to keep you warm. And if it's hot out, then your skin is doing what it can to sweat to keep you cool. But while your core temperature remains stable at 98 degrees Fahrenheit, your skin is fighting a frantic war with the particles of air that surround it. If you remember previously, particles that vibrate have thermal energy which can and will be transferred to any matter that the particle bumps into, until the two particles share the same thermal energy or temperature. Now, in regards to what happens on the surface of your skin, when it's hot out, or at least hotter than the temperature of your skin, the hot air outside bounces onto your slower moving skin particles until those particles in the air and on your skin are bouncing around with the same speed. When it's cold out, it's your skin that transfers energy to surrounding cold air until the energies of the two bodies match. And if your body is doing its job remaining at its equilibrium temperature of 98 degrees Fahrenheit, then your skin will tend to move to 98 degrees Fahrenheit, and so will the blanket of air particles immediately surrounding your skin. Whether we're aware of it or not, our bodies are constantly dancing with the air around us to keep it a warm 98 degrees Fahrenheit. Everywhere we go, we're surrounded by a ground of heated air we've created. It's like wearing an extra shirt that fluctuates with the temperature of your skin. However, when you move around, or when the world moves around you, the fragile layer of air particles covering your skin is disrupted. Some air molecules hitching a ride on the surface of your skin fly away, and new ones come in to take their place. Your body has to reheat or lose energy to these new air molecules. Standing still on a windy day and standing in front of an indoor floor fan have the same effect of disturbing the thin layer of the surrounding air. With every disturbance in the loose blanket of air we wear comes a new song and dance of energy exchange. So where exactly does wind chill fit into all of this? Though it's mostly associated with especially cold weather, wind chill broadly describes a phenomenon present whenever the ambient temperature is colder than the temperature of your skin. Specifically, wind chill is concerned with the general process of your body heating colder molecules of air up to the temperature of your skin. Wind chill, in essence, describes the effort your body exerts to continue heating the atmosphere surrounding your skin to keep it in an equilibrium with your skin and your core temperature. When the air is especially cold, your skin has to work hard to bring air molecules up to 98 degrees Fahrenheit. But where the human body struggles is not with frigid ambient temperatures, but with episodes of strong wind and gusts on a cold day. On cold and especially windy days, the molecules of air clinging to your warm skin are constantly ripped away. Your skin continually transfers energy over to icy molecules of air that are sure to be torn away only moments later. The cells in your body kick into overdrive to keep your internal temperature at 98 degrees Fahrenheit. Still, with its exposure to the elements, your skin struggles to keep up, and your own surface temperature begins to drop to match the average temperature of the surrounding air. At this point, the familiar sensation of freezing starts to kick in. Since not much is keeping the surrounding particles of air in place, wearing clothing over your skin can help to maintain the integrity of the layer of heated air surrounding you. Heavy windbreakers, sweaters, and clothing, as well as scarves, gloves, and face coverings, limit the effects of wind chill. That is, they limit the weather's ability to tear your heat away from you. Wind chill directly measures the cycle of losing heat to strong winds, not because the wind is cold, but because the wind bumps heated air particles away from your body. In fact, this process of transferring heat over to a constantly shifting layer of air molecules is exactly how one blows on soup to cool it down. Sure, your breath is probably cooler than the soup, but the soup is actually cooling off by transferring its heat energy over to the constantly displaced layer of air above it. When you blow on soup, the soup loses its protective layer of hot air, and it has to lend more of its heat energy to the new room temperature molecules that just moved in and over the bowl. Yet despite posing as a temperature, wind chill doesn't necessarily depict a measure of energy or heat found in any given body. For example, if the ambient temperature outside is above freezing, a glass of water will never freeze, even if the given wind chill temperature is below freezing. In short, wind chill depicts a process of heat loss and does not capture a measure of energy. Why wind chill shows up on the daily weather as a temperature and not another unit? The modern degrees Fahrenheit version of wind chill originated in 2001. Previous models and representations of wind chill factor existed, but they were either rejected or tweaked. Before the current wind chill measurement in degrees, wind chill statements issued to the public appeared as 3 or 4 digit numbers with units that were rather difficult to internalize. Imagine having to decide whether to wear a light jacket or a heavy parka, and the weather mentions that it's 57 degrees Fahrenheit outside, with a wind chill factor of 1400 kilocalories per hour per square meter. 1400 kilocalories per hour per square meter was the threshold for frostbite, yet it's hard to imagine anybody seeing that unit for the first time would bat an eye. Compare that to the modern scenario, where it's 57 degrees Fahrenheit outside with a wind chill of 31 degrees. The issue with the previous model is that its measurements had very little to no psychological impact on people. We follow the weather to dress accordingly, and when the weather fails to leave an impression on us to change into something more appropriate, then that particular weather measurement should be revised. This is what the Joint Action Group for Temperature Indices, a task force consisting of scientists from the National Weather Service, the Meteorologic Services of Canada, and the academic research community, believed at this turn of the century with the new wind chill factor model. Yes, wind chill appropriating the form of temperature is perhaps scientifically misleading, but it is taking advantage of our familiarity with temperatures like degrees Fahrenheit and Celsius. It hijacks our brain psychology to do what weather reports are meant to do, to have us bundle up to beat the heat. Or if you're anything like me, you ignore the weather entirely and sacrifice comfort for style. Hey, Taylor Swift here. Well, that's the end of this video. I hope you learned something today, and as always, many thanks for taking the time to watch. Have a good one, take care of yourself, and most importantly, drink plenty of water. See you next time.